Okay, so good morning. Before I start, just wanted to point out that I think I've uploaded a couple of problem sets uh, on Teams in the file section, so you can get started. Um, I'll be taking questions a week from now. Mm, Try it out on your own, and then we'll take a look at them after you've sort of given it a shot. The second thing is the minor has been announced. I believe it is on September 20th, uh, which is uh, about a couple of weeks, or is it exactly a couple of weeks from now? Um, so the exact format of the minor uh, is still something that I'm thinking about. In view of the mass copying going on, I have been thinking that it is much better for me to conduct the minor one on one. So rather than have a written test, I mean, my experience last semester was that I could easily see that there were groups of seven, eight people, literally identical. It just wasn't worth my time to make an issue out of it. But having learned from that, this time I will be conducting an exam almost certainly on a one-to-one basis. Just how I do it, I will decide between now and next Monday, probably before that. So be prepared for. It will not be a long exam. I mean, I might ask you to, you know, give you a paper to read and then just start querying you on it. That I think seems to be the most likely, or I might give you some problems from the homework. Um, you know, seek more detail on how you did it, why you did it. That I think I need only 5, 7 minutes to figure out whether you really know what you're talking. So is that part clear? We're done with that part out of the way, then I can move on. So homeworks are on the in files, and a brief note about the modalities concerning minor one. Is that part clear?
Yes, sir.
So any questions about what we have covered so far? I mean, um, actually, I could spend 5, 10 minutes fleshing out before I go to the next topic. Um, so, I covered this dual limited regime last time, and pointed out that um, this is actually also related to today's lecture. So I want to flesh this out in more detail. Say, take this case over here, which we did. Uh, this is the case of. I showed you data for uh, transition from carbon limited to nitrogen limited, and then discussed the transition from carbon limited to oxygen limited, saying the principle is the same. Uh, Basically, the transition is not abrupt. It doesn't abruptly go from carbon to oxygen, but it goes through an intermediate dual limited regime where it is limited by both carbon and oxygen. And this is the regime in which the cell is kind of adjusting to the oncoming change in the limitation, and therefore you see changes in the yields. Uh, Now, I'd like to sort of just uh, make you think a little bit about something that I have already said. and see if you can understand what's going on here. So keep in mind that this is a chemostat study performed at a fixed dilution rate. And on the left side, the only thing limiting is the availability of carbon. Given that fact, I want you to explain to me, if you can, the data that we are seeing. So we have fixed the dilution rate and we are changing the concentration of the carbon source. Okay? This is the opposite of what I showed to you when I discussed the Monod model, where we kept the feed concentration fixed and increased the dilution rate. So if you go back and take a look at your notes on the Monod model, you will find the graph that is of this type. The feed concentration is fixed and D is changing, and what I showed to you was that the substrate concentration stays low and then goes high, right? And then doesn't change because the cell concentration becomes equal to 0. And here the cell density kind of goes down like this. So this is how X changes according to the Monod model, and this is how the substrate concentration changes. So this is the picture, and this is what we call this specific dilution rate was what we call the critical dilution rate or the washout dilution rate, beyond which cells cannot be sustained because you are flushing out at a rate faster than the fastest rate at which the cells can grow. Now I'm asking you the question which is the opposite in some way of this or the complement of this. Way to the left side, you are actually increasing the feed concentration at a constant dilution rate. Can you explain why the cell density is increasing? I mean, this is the same model. I've just changed the parameter that is fixed and the parameter that is changing. The first question is maybe even simpler than that. The first question is, this over here, maybe I should use the same color. This line over here, which represents the concentration of the carbon source, S, it is constant. Can you explain why it is constant in terms of the model? So keep in mind, dilution rate is fixed, feed concentration is changing. Did you follow the question? I mean, is there any ambiguity regarding the question?
So I guess the question isn't very clear, at least to me.
Well, the question is, can you explain these trends using the model? I'm telling you that S is constant and X is increasing linearly. I even showed you the data last time that that's how the data happens to be. Right? We did it for the transition from carbon to nitrogen limited regime. I thought I showed, here is the data. Let me repeat it just in case you think I'm fantasizing. So here is the data. You can see that the biomass level, top panel, is increasing linearly, right? And the methanol level, which is shown in the red curve on the top panel, is basically constant on the left hand side. And the ammonia level is coming down linearly. Can you explain this data? Is the question clear now or no? I mean, on the left hand
Sort
side,
of, yes, sir.
on the left hand side, you have a single limitation. When you have a single limitation, you can use the Monod model. I told you that the model only fails in the middle because you have dual limitation. But on the left hand side and the right hand side, the model works fine. So, based on the Monod model, can you explain the trends observed on the left hand side? Is that question clear or still not?
So it is clear, but we're thinking about the answer.
So, you have to use the same model. The only difference is that instead of changing D at a fixed feed concentration, you are now changing the feed concentration at a fixed D. But the model is still the same. So my first question is, can you understand why the residual substrate concentration will be constant?
So I guess because microbes are continuously consuming substrate, so they are maintaining the minimum concentration of the limiting substrate because that is the only barrier in their growth.
I mean, that's kind of verbally on the right track, but I'm looking for an explanation in terms of the mathematical model, which we have already solved. Mm, I should emphasize that you should really practice uh, the numerical problems a lot more. Let me go back now. Go back to your. Uh, go back. What I'm saying is that on the left hand side, the system is limited by the availability of carbon, and Monod model applies? Well, first thing to see is, and two questions. I want to know, why is S constant and why is X increasing linearly? Both of these are straightforward. Well, the first one is that if you go and take a look at the mass balances, you will see that the mass balance for biomass at steady state reads mu minus d times x, which means that if d is sufficiently small, and therefore mu can be equal to d, mu is equal to d, so that implies mu of S is equal to D. Now, if D is constant, what do you think the value of S is? I mean, is it hard to see that? Can you see if a function of S is equal to D, where D is fixed, can S
So
change?
then S is constant.
Huh?
S is constant if D is
Yeah.
constant.
That's not fact. We know that this has the solution. Ks S equals Ks times d over mu m minus d. And I also pointed out that basically S will be very, very small for various d until d becomes equal to mu m. In fact, I showed the graph last time that this means that S is totally a function of d. It is independent of, so I'm plotting now the solution. Basically be some number that is, let me use another pen, really, really low, and then it rises very fast. So basically, if you're operating at any sufficiently small d, you will get some imperceptibly small value of S. And that is simply because this Ks is very, very small. So as long as d over mu m, as long as the second factor, right, the second factor is not too big, S will be on the order of Ks, which is on the order of micrograms or milligrams per liter. It is only when d over mu m minus d becomes very, very large, and that is only when d becomes comparable to mu m, that S will become very, very large. Okay? So that explains why at fixed d, S is constant. Now, the next question is, can you explain to me why X goes up linearly? So I've just explained that S is constant. Now, can you explain why X goes up linearly in this system? Do you remember the formula for the biomass concentration in a chemostat? Total silence. Yes, no, maybe.
Yes, sir. So it was X naught plus Y of Sx into S naught minus S.
No, that wasn't batch cultures. Talking about chemostat.
Oh, sorry, sir.
D upon RS SF minus S.
But that, what is D over RS?
equals to that was YSX observed.
Uh-huh. So, um, actually, in the Monod model, you can go and take a look. X turns out to be simply YSX multiplied by SF minus S. Now, you can see that if this experiment was performed at any D that was sufficiently small compared to mu m, that you can see from this figure over here, then S is like really, really small. So, which means that this term is actually really, really small, which means that X is essentially approximately equal to YSX times SF. So what this is showing you is a rather curious phenomenon that it's interesting. The cell density, right? So first point, the substrate concentration inside the chemostat, the residual concentration, depends completely on the dilution rate. It is completely independent of the feed concentration. You can see that, right? Because S is equal to Ks d over mu m minus d. It's worth pausing to reflect on this. This is saying that no matter how much glucose you pump, your feed concentration can be 1 gram per liter, 10 grams per liter, 20 grams per liter, no matter what you add into the reactor. The residual glucose concentration in the reactor will remain unchanged provided your dilution rate is fixed. It's a little counterintuitive, right? Now, what's going on here? Well, you can see that this is not magical because the next equation shows to you that basically what happens is the substrate concentration remains the same, but the density of the cells increases in proportion to the feed. So the density of the cells keeps on rising. And the higher density of the cells ends up consuming this extra substrate that you have pumped into the reactor in such a way that the concentration of the substrate in the reactor remains the same. Is that clear? I mean, follow what I'm saying?
Yes, sir.
Okay. Now, let me also ask you. It's a little bit. Uh, so we have not done gas balances, so it's difficult for me to ask you why the um, um, DO level is decreasing. But if I am to go back to the graph here, this is the transition from carbon to nitrogen limitation. Can somebody explain to me why the nitrogen concentration is decreasing? First, explain this to me intuitively.
So because as cells grow more, they make more and more protein. And like they require more nitrogen from the surroundings.
That's right. So essentially, because you can see, if you're going to create, remember, this experiment was done at a constant feed concentration of the nitrogen. The only thing that is being varied in these experiments is on the x-axis, you are increasing the feed concentration of the carbon source. So the feed of ammonia into the reactor is fixed. Okay, that's a fixed number. Now, as you move to the right, as you increase the feed concentration of methanol in this case, you have just seen that the concentration of biomass becomes higher and higher. Well, this higher biomass concentration means that the density of the cells is increasing, and these cells need nitrogen, so obviously they consume more nitrogen. And because they consume more nitrogen, more of the feed, more of the nitrogen in the feed will get depleted. But can we make this more precise? Can we write a mass balance uh, and see how this happens? So let me actually start by doing this. See, the Microsoft pen is terrible. I don't know if it will come through, but let's start and see. Let's say this is D multiplied by, we're now writing the mass balance for nitrogen. So this is, let's say N is the concentration in the reactor, N sub F is the concentration in the feed, then the mass balance for nitrogen reads D N dt equals D times NF minus N minus Rn. This is just terrible. Rn times X, where Rn is the specific ammonia consumption rate. Okay? Now, according to Monod model, right, I want to, so what you have just answered, I want to make that more precise. Now, what do you think Rn is? Can we estimate Rn based on Monod's model, which says that y xs times s plus y xn times ammonia plus dot 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 goes to x plus dot dot dot, and this is mu. Can we estimate Rn?
Rn equals to yxn times mu.
That's right. So this is nothing but yxn times mu. But what is mu? Mu equals
Um into n upon kn plus n.
mu is equal to D.
Yeah.
If I cancel out the D now, this whole thing is equal to 0. If I now cancel out the D, I cancel out the D, I cancel out the D, what do I get? I get X, I get NF minus N, right? Equals X multiplied by YXN. I mean, is that part clear? Basically, you are saying NF minus N is equal to YXN multiplied by X. Is that part clear?
Yes, sir.
So that means the decline in the nitrogen concentration from the reactor, from the feed into the reactor, is basically directly proportional to X, right? Is that part clear?
Yes, sir.
But we have just derived an expression for X. Plug that in. First of all, so you can see now the data is exactly in line with that. As X increases, the concentration of ammonia declines from its feed value, right? It's going down linearly. So, I mean, another way to state this is NF minus N equals Y xn times X. You already know an expression for X. We found out that X was equal to y sx multiplied by sf approximately. That's it. You're done. So you can see that nf minus n, these are all constants. So you can see that nf minus n is essentially directly proportional to sf. That's the result you're looking for. That part clear?
Yes, sir, it is.
Uh-huh. Now, I think that now that I have done this, I can move on to, so take the numerical problem seriously, because unless and until you solve problems, you will never be able to uh, figure out these things. I mean, it is only through practice that you will figure out what is going on. So the exam will pretty much be questions of this kind, right? I mean, given something, tell me why this is going on by using uh, the model that we have developed. And if the model doesn't work, why doesn't it work? So coming back now to the topic that I want to cover today, um, this is actually an important topic uh, from the point of view of application. So in your syllabus, this topic is mentioned as medium formulation and design, and this topic actually receives very little attention in the books, because I think this is a topic of practical sort of interest. But it turns out that it has profound repercussions, and I mean, I would argue that about more than 50 to 60% of the papers, at least in certain areas of biology, they produce nonsense by ignoring this area. So the basic idea behind this area is actually quite simple. Uh, Let me go back to what I said right at the beginning of the class. When we have a single substance or a single nutrient that is limiting the growth of a culture, it does not happen on its own or by accident. It is by careful design of the medium. That medium has been designed such that all entities, all nutrients, except the one that you are interested in making the limiting nutrient, are in excess. So, what I'm going to cover today is basically uh, uh, how that is done. But I'm taking all this from a paper which I'm giving to you, and maybe I'll just briefly go through some of the key. This is a review of the key points so that you understand what is happening here. I mean, the ultimate calculations are really, really straightforward, but I'm repeating. And maybe it's also helpful that some of the things that I have said will be shown by actually pointing out the data. So, um, okay. So, first point is uh, to describe what is the idea of a limiting nutrient. So this is all taken from this paper, which I will send to you. It is a paper, I believe, from 2009. 2009, yeah. Um, it's a chapter from the Encyclopedia of Microbiology. Um, so maybe I should begin by just pointing out the basics. So, has this been covered in microbiology? What is a defined medium? What is a complex medium? What is a
So
Sir,
very
not yet.
briefly. So very
Not yet.
briefly, but not in depth.
Yes.
So what is done in microbiology? Can you just flesh out for me? Even the medium is not done. I mean, do you
No,
spend
sir,
most of it?
we did the media, but like not in depth. Like we just briefly touched upon like the different sorts of media.
Uh-huh. Okay, so uh, the the first point to be made is that the type of medium you design kind of depends upon the type of organism that you are working with, and the organisms are classified into four categories depending upon uh, manner their nutritional needs are met. So this classification, and what is being shown in table one, is that broadly speaking, there are, if you will, four types of organisms based on what is the energy source, what is the electron source, and what is the carbon source. Okay, these are the three. You have an energy source, you have a carbon source, and you have an electron source. And depending on what these are, you can have different types of organisms. These different types of organisms then require different types of media. So, if the energy source is light, as is the case, for example, for certain algae, um, then they are called phototrophs. If the energy source is a chemical, for example, E. coli, that actually the energy source for it is, you know, a carbon source like glucose or succinate or what have you. Then what you have are called chemotrophs. Now, the electron source can be either a reduced, it's always a reduced compound, the electron source. The reduced compound can be either inorganic or organic. Almost all the examples that we do have organic compounds, but I just want you to keep in mind that they can be inorganic compounds as well. And whenever the electron source is an inorganic compound, you will see the word litho. Okay? And the last category is carbon source, which can be either CO2, literally cells. There are certain cells that can incorporate carbon dioxide. They are called autotrophs. And then there are others that require reduced organic compounds. Those are called heterotrophs. So whether it is light or chemical, they use photo or chemo. So I mean, let me just use the pen to see. So this photo is describing the energy source. Then this litho is describing the electron source. And finally, this auto is describing the carbon source. So likewise, in the next case, the photo is describing the energy source, and then the litho is describing the electron source, which is an inorganic compound, and then finally, the hetero is describing the organic compound that is the carbon source. So you can see uh, things can be going to the next one. Things can be then the next one. Chemo describes the energy source. Litho describes the fact that you have an inorganic compound as the electron source. And the last one says that it is auto because we have CO2 as the carbon source. Now, almost all the work that is done, the large majority of the practical work that is done with the last case, which is it's a chemical energy source, right? A organic compound as the electron source, and also an organic compound as the the same organic compound is the electron source as well as the carbon source. So, for example, glucose is not only a carbon source, it is also the energy source. That part clear? I mean, it's basically the same compound. So this is the simplest. The last category is the one that you must have seen in the lab. The other ones are considered kind of exotic. They are important in nature, and they're also important in some applications, but you don't see them a whole lot. The next thing you need to know about nutrients is shown here in table 2. So the nutrients are typically also classified based on how necessary they are for the growth. So uh, basically, the ones that are always essential. I mean, you need them. There is no way they will grow without these. These are classified into, so basically, carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, potassium, and magnesium. If you don't have these, guaranteed there will be no growth. Every organism needs these elements in some way, shape, or form. And they are classified into major elements and minor elements. This is the classification based on the quantities required. You need a lot of carbon, a lot of hydrogen, a lot of oxygen, and a lot of nitrogen for reasons shown in table 3, which shows the elemental composition of biomass. You can see that basically the second column, which is showing you the percent dry weight, almost half of biomass is carbon, 50%. This is the reason why it is a major element. 20% is oxygen, 10% is nitrogen and hydrogen. So this is why they are constitute as shown in table 2. This is the reason why they are called major elements. The rest of them, like phosphorus, sulfur, potassium, so I'm pointing out, maybe I should mark it out. These 4 are the major elements, and the next 4 are called, these are essential. Carbon, oxygen, nitrogen, and hydrogen are essential major elements. Phosphorus, sulfur, potassium, and magnesium are essential minor elements. Then class 2 is what is mostly essential most of the time. This is a bunch of elements like iron, calcium, magnesium, cobalt, copper, molybdenum, and zinc. And then the last in the last 2 categories, class 3 and class 4 constitute what are called trace metals. They are added in very, very small quantities. I mean, literally in milligrams per liter. And class 5 are for certain strains. You simply can't get away with supplying basic elements. You actually have to provide fully formed compounds like amino acids, like fully formed purines and pyrimidines, fully formed vitamins, hormones. These are called growth factors. And in some, like yeast, for example, right? I mean, there's a certain yeast we work with. If you don't provide it with the vitamin biotin, you'll see no growth. That's it. It will not even grow. Um, so that sort of gives you a brief overview of what are the elements that are absolutely essential, what are the elements that are mostly essential, and then the, the trace metals that are required in very, very small quantities. You notice that in class 4, he says very rarely essential, difficult to prove. What he means by that is that the quantities required are so small that you can't even tell if they're necessary or not because you can't even maintain. I mean, so even if you take relatively pure water, it may have these quantities, or when you add some salt, the impurities from it might fulfill these requirements. So we're never going to be able to find out whether they are absolutely essential or not. Okay, is that part clear? And maybe I should just point out this is related to what we have already done. Um, Notice that the percent uh, of carbon, oxygen, nitrogen, and oxygen, which is 50, 21, 12, and 8 here, also kind of explains what was given to you in an earlier lecture as the average cell composition. Average cell composition was given to you as C. This is average biomass composition. I should not say cell, I should say average biomass. This was given to you in one of the earlier lectures where I said that the constant composition of biomass is pretty constant. This was given as C H1.8 O.5 N.2. Now, if you go back to this column, and this is in weight, percent of weight. If you convert this to moles by dividing 50 by 12, and then the percent oxygen 21 by, for example, 16, and the percent nitrogen 12 by the atomic mass of nitrogen, which is 14, and the one for hydrogen, which is 1, you get the ratios. Carbon is 1, hydrogen is 1.9, oxygen is 0.3, and nitrogen is 0.2, which is pretty close to the composition that I gave to you. So you can see where this composition is coming from. Is that part clear? Follow what I'm saying?
Yes, sir.
Okay, so the next question is, why is the elemental composition of biomass so constant? I mean, it's a kind of a mystery, right? I mean, all this fancy biochemistry packing, 7 kilos like a door stopper, and at the end you find out that the composition doesn't change. Well, the reason is given right here. I mean, let me read it out to you. He says that the relative composition of microbial biomass with respect to the major elements. So the relative constant composition of microbial biomass with respect to the major elements results from the fact that most of the dry mass, typically some 95%, is made up of a limited number of organic molecules, and only a small fraction can be attributed to monomers. So as shown in the table over here, this is showing you the composition of a cell in term the macromolecular composition of a cell, not elemental but macromolecular. So this is saying by percent weight, you have 55% of the total weight as protein, 21% of the total weight is RNA, 3% of the total weight is DNA, and then the remaining ones are like peptidoglycans and phospholipids and so on and so forth. You can see that these macromolecules make up virtually all of the dry weight. And since these macromolecules have a pretty well defined carbon, hydrogen, oxygen, and hydrogen composition, you can actually, the elemental composition of protein, RNA, DNA, peptidoglycans is relatively well defined. So if the macromolecules have a relatively well defined elemental composition, and they comprise relatively well-defined percentages of the total dry weight, then you should not be surprised that the elemental composition itself is well-defined. Is that part clear? Making sense to you?
Yes.
So this part you should take a look at biochemistry. But I have not said clearly, I'm taking this at face value, is that even though you have hundreds of different proteins, right? I mean, thousands of, maybe millions of different proteins, um, their elemental compositions are relatively well defined. They don't vary a whole lot. Likewise for RNA, DNA, and phospholipids. Okay. Now I'm going to skip this part. I'll just mention one thing. This is worth talking about. We have talked about two parameters when we discussed the Monod model. We have talked about not actually two. We have talked about three parameters. One is mu m, which is the maximum growth rate. The other is Ks, which is the saturation constant, and the third is YSX, which is how much biomass do you make per unit gram of the substrate. Now, the first two parameters, mu m and Ks, they're completely, so far as I know, unpredictable. By unpredictable, I mean that different organisms have different values of mu m and different values of Ks. Mu m, if you remember, this mu m and Ks, they appear in the expression for the growth rate as mu m times S divided by Ks plus S. The, the YSX, on the other hand, is like a stoichiometric coefficient. Now, the point I'm making is that these mu m and Ks, right, uh, impossible to predict. They're impossible to predict. Nobody knows. If I give you a strain and say, tell me randomly what the mu m and Ks is, you just have to measure it. There is no way of predicting it. But this YSX, actually, it turns out, is fairly predictable. At least in the case of these carbon sources that we work with, like glucose or succinate or glycerol or acetate. And why is that the case? So let me show you the data. Well, no, let me basically first make the point. Roughly speaking, uh, the more reduced the substrate, right? By the more reduced meaning, you can calculate the oxidation numbers. That is that number. Do you remember that from physical chemistry? Oxidation numbers.
Yes, sir.
Huh. So based on the oxidation numbers of carbon, you can actually calculate how reduced the compound is. And roughly speaking, the more reduced the compound, the higher the biomass yield. Now, why is that? Roughly speaking, the more reduced the compound, the more energy you will get by oxidizing per gram of that substance. Right? So the more reduced the compound, the more energy you will get per gram of oxidation of that substance. So since very little, so supposing I have a very reduced compound, then by oxidizing only a small fraction of it, I will generate enough energy to convert the remainder into biomass. Whereas if I have a highly oxidized compound, then when I oxidize 1 gram of it, I get very little energy. Since I get very little energy out of oxidizing 1 gram of it, then a significant fraction of this oxidized compound has to be oxidized before I can reduce the remaining biomass into the remaining substrate into biomass. Is that making sense? I don't know if I said it right. That making sense? Do you understand what I'm saying?
Yes. So basically, like for example, if a strain has say methane as its energy source, so it will produce more energy per gram of methane than it would have produced per gram of say glucose
I mean,
because carbon is
uh,
much more reduced.
that's it. That's the essence of it. You need energy to convert a carbon source into biomass. That much is clear. Now, if the same carbon source is also providing the energy, right? Then you have to break down some part of it to generate the energy, and that energy has to be used to convert the remaining part into biomass. Well, the more reduced the compound, the more energy it'll degrade, it'll produce per gram of it. So because if it produces a lot of energy per gram, then a lots of it can be converted into biomass, because by oxidizing only a small fraction of it, you got a lot of energy enough to convert it. Let me read it out, right? This will become, so I am reading um, the highlighted part. It says typically heterotrophic cells utilize the same carbon source for both purposes, oxidizing a part of it to carbon dioxide, a process called dissimilation, and using the energy derived from this oxidation to synthesize cell material from the other part, assimilation. So basically, the same substrate is being used both for dissimilation, which is the production of energy, as well as assimilation, which is the conversion of that carbon substrate into biomass. The ratio of dissimilated to assimilated carbon is essentially dependent on the degree of reduction of the carbon substrate used. The more oxidized the carbon compound, the more of it that has to be dissimilated in order to provide the energy to drive the synthesis processes, and the less of it that can be assimilated. That's, is that part clear? I think I can't. I'm really belaboring this point.
Yes, sir. It is.
So you got the point. And now I'm simply going to show you the data. Now, this data is showing you, on the y-axis, it is showing you how much biomass you get per gram of substrate. This is basically what we have called YSX. This is grams dry weight produced per gram of substrate. And this has been shown for various carbon sources. On the x-axis, they are showing you the heat of combustion, which is a measure of the degree of reduction. This is a measure of the degree of reduction. The more reduced the substrate, the more the heat of combustion. That means when you burn it, the more kilocalories you will get per gram of substrate. And what they're showing you over here is that for highly oxidized compounds, which are way to the left, as you increase the degree of reduction, the more the biomass you generate. Okay? Until you get to a point, there is like a critical point here. Beyond this reduction, it appears, so there is like an upper limit to how much yield you can get. Once you start dealing with compounds that are more oxidized than a certain point, then you reach a certain, so there seems to be some kind of a limit. And this actually has also been explained by people by using the second law of thermodynamics. People claim that this represents some sort of a limit that comes from the second law of thermodynamics. So, I mean, I think your class has not done thermodynamics, has it? I mean, in any serious way?
No, sir.
So we'll skip that part, but you get the basic idea. Um, Now, I think that basically takes me to the point where I just have to review two small points here. The first is, this is a review, which I've already done. What happens when you grow cells in a shake flask? If you remember, I told you that basically they grow at the exponential growth rate for almost all of the growth. You can see that this is divided into three regions. The graph here, this is 1, this is 2, and this is 3. In region 1, there is no limitation at all. Everything is available in excess. And therefore, the cells execute exponential growth with their maximum specific growth rate mu m. That's where you get the equation dx dt equals mu m times x. This is where you have x dot as equal to approximately equal to mu m times x, which gives you exponential growth. Now, way to the end, you know, in the region which he has denoted by 2, that's the region where the substrate concentration now becomes comparable to Ks, and therefore the specific growth rate declines from its maximum value. This is the region where he calls it kinetic limitation. The rate of growth slows down. You can see that, right? I mean, it's slowing down, and then gradually, once you reach the region where he calls stoichiometric limitation, the growth has completely become equal to zero. There is no growth at all, and the growth curve flattens out. That last region is what he calls stoichiometric limitation, and this is the region where the biomass concentration is x0 plus y. We called we have used the notation yxs. So for us, so keep in mind, region 1, no limitation. Region 2, kinetic limitation, which means that the specific growth rate slows down. Now, I'll show you the data in a minute. As I pointed out to you, in most cases, region 2 is so thin that you can barely see it. You basically jump from region 1 to region 3 in no time at all. And that is why we are able to use the approximate model. You know, the approximate model, we just allow it to grow exponentially. And at one point, we just say, okay, stop. We have reached stoichiometric limitation or stationary phase. This is just a repeat of what I have told you already. So is that part clear? Just
Yes, sir.
some new jargon. This is kinetic limitation and stoichiometric limitation. This is the jargon they use. Stoichiometric limitation means this is determined by how much substrate you put at the beginning. Kinetic limitation affects the speed of growth. Stoichiometric limitation determines how much biomass you make. So kinetic limitation has to do with rate. Stoichiometric limitation has to do with biomass amount. Okay, so here is real data. And this real data is intended to show you that the middle region, which you can see, the middle region is where the graph kind of slows down and becomes slowly equal to zero. I'm talking about the dashed curve here, this one. Notice how the slope is slowly decreasing to zero, right? This kinetically limited regime in practice is often not observed. Like, take a look at this. This is real data. Can you see where it is slowing down? You can barely see it. Basically, it just goes straight up and then just flattens out. You don't see the region where it is kinetically limiting. And the reason for that is that basically the limitation occurs at a substrate concentration that is so low. Go back here. This region happens simply because this region happens when S is on the order of Ks, right? Because, and this is where S is much bigger than Ks. Now, suppose Ks is on the order of 10 micrograms per liter or 10 milligrams per liter. These are really small quantities, right? This substrate concentration, so then that means that you are going to observe the kinetic limitation when S is on the order of 10 micrograms or milligrams per liter. This substrate concentration is so small that this region, keep in mind that in this region, the biomass concentration is really high It is S that is really, really small. So because the biomass levels are so high, they eat the stuff up in no time at all. I mean, if you give 1 gram dry weight per liter of cells, like 10 milligrams per liter of substrate, they will clean that out in like 10 seconds. So that is why this region is very, very small. Is that part clear?
Yes, sir.
Okay. So I think I've now I mean this is all leading up to okay. So I don't know. I mean, I'm try to read some of the stuff on your own. So let's get really to the determination of the medium now. I'm skipping a little bit here and there. I'll see if I can come back to the parts that I have missed. Well, the idea behind the development of a medium is pretty straightforward. Let me do that. Um, um, actually, by taking a look at the so he says that basically whenever you want to design a medium, the first thing you need to know is approximately what is the maximum biomass level that you will have in your experiment. That you need to know. You know that I expect my biomass levels to be so much, because those then determine how to make your medium. And what he talks about making the medium here is you have to decide what is your limiting nutrient. You know, you have to decide. So you're making the medium in order to have a particular limiting nutrient, which is almost always, for us at least in this department, the carbon source. So it's glucose or what have you. Now, the way you do that is actually we're actually using in a way the Monod model, the stoichiometric equation. It'll become clear in a minute. So basically, uh, supposing I know that, write it as straightforward. So supposing I know that I want X max, this is my maximum quantity of cells, and let E be any element, okay? And he uses the notation Y E, this is his notation, Y E slash X. This guy's notation is how much of that element do I have per gram of substrate, per gram of biomass. So this is in first quantity is in grams dry weight per liter, and the second quantity is in grams per gram dry weight. So that's grams of element per gram dry weight. So this element could be, for example, nitrogen, or it could be phosphorus. So I know I need so much dry weight per liter. This I know in advance. And where do I get YEX from? I know the composition of biomass. Biomass contains so many grams of nitrogen per gram dry weight. So that means I need X max multiplied by YE slash X. I need at least this much nitrogen per liter in order to just get X max biomass. Is that part clear?
So,
Yes, no, I didn't get it.
yes, sir.
So now X max multiplied by YEX is the amount of, this is the bare minimum you need to sustain the biomass. Okay? If that particular element is not the limiting one, then you want it to be in quantities more than this because it is supposed to be in excess. So then you also multiply it by, so this X max, let's say star, and this is multiplied, also multiplied by an excess factor for that element, which he calls Fe. So X max times YEX is the amount that is required simply to sustain the production of biomass. And if this particular element is not limiting, then multiply it by an excess factor of Fe, which is some number greater than 1. It could be 5, it could be 10, depending on how much excess you want. So that is what is shown over here in this formula. If you take a look at equation 3, right, he's writing the same formula, except that he's writing it in some obscure reciprocal way, which I find kind of irritating. This equation can be written as X max. Now, he has divided it by Yx slash E. Yx slash E denotes how much biomass is produced per gram of element, which seems to me to be a really stupid quantity to work with. Much more convenient would be the quantity Ye slash X, which is how much element you have per gram of biomass, and then multiply by Fe. So this quantity in brackets is, this is concentration of element. I should just say concentration of element E required to form X max grams dry weight per liter of biomass. So this you can think of as the bare minimum required, and then you have to multiply it by Fe, which is some number greater than 1. So this is how, this is a really, really crude sort of way of calculating. And now let me show you a real example of this. So where this is actually used. So here is the design of a medium. So this is the design. This is showing you the design of a carbon limited. So here you want carbon to be the limiting element. All other things are to be in excess. So what you will find is that this factor Fe will be bigger than 1 for all elements except carbon. How much bigger? We'll just see in a minute. So he says design of a carbon limited minimal medium allowing the production of 10 grams per liter of dry biomass. So X max is already given to us. This is 10 grams dry weight per liter. So in this formula 3, X max is given to us. Now, on the left hand side are the medium constituents. Each of these medium constituents has been provided in order to fulfill a certain function. It provides either carbon or nitrogen or phosphorus. And so notice that in the second column, he is defining what particular elemental requirement is satisfied by that medium constituent. So glucose is a carbon and energy source. Ammonium chloride is a nitrogen source. The sodium phosphate, dihydrogen phosphate, is the source of phosphorus. KCl is the source of potassium, so on and so forth, right? This is the way he is. These are the medium constituents. And the question is how much of these to take? Well, we will use formula 3 to estimate it. Now, X max is already given to you. The next thing we need is this quantity Yx comma E, which in my opinion should actually be expressed as Ye slash X. But anyway, he has chosen to give it in that way. This is basically giving you the elemental composition. So if you can see Let's see. This quantity is given as 8. It means that 1 gram dry weight of biomass has 1 over 8 grams of nitrogen. That part clear? Similarly, 1 gram dry weight of biomass has 1 over 33 grams of phosphorus. So this is basically giving you the coefficient Yx/E. The next one is giving you the value of Fe. Now, how he chooses Fe, I'll tell you in a minute. But you can see that except for carbon, all the quantities are in excess. All the quantities except carbon are bigger than 1. And the basic rationale for choosing these numbers is the more ill-defined, see, quantities that he knows very well. For example, he knows the nitrogen composition of biomass very well. He has a lot of confidence in this number 8. He also has a reasonably high level of confidence in the number for phosphorus, in the number for potassium, in the number for, these are the elemental compositions of biomass. Wherever he has a good deal of confidence, he uses 3 to 5 as the excess factor. These quantities, starting from, calcium, he has a low level of confidence and therefore he uses them in a large excess. So this is a standard engineering trick. Whenever you don't know something very well, you introduce a higher safety factor. So basically he knows Yxc, this is derived from the composition of biomass. The excess factor is determined based on the degree of confidence he has in these Yxcs. So once he has Yxe, right? He has Yxc, he has Xmax, he has Fe. He can just put this into equation 3 and that tells him what is the mass of the element that is required in order to have the desired biomass. Once he knows what is the mass of the desired element, he can also calculate the mass of the compound that is required, right? Because, for example, in this case, how much carbon do you have in glucose? Well, glucose is CH2O, so carbon is 12, hydrogen is 2, and oxygen is 16. So basically, carbon is 12 divided by 30. So that means that if you need 10 grams per liter of carbon, you have to use 25 grams per liter of glucose, which is the 30 divided by 12. Is that part clear?
Yes, sir.
So again, this is the best way is to practice. So this is the way in which you first establish the composition of your medium. This is how you build a medium, going backwards. Okay. Having done so, you now want to check if the medium works, and that is done by doing this experiment. Basically, the simple principle is, maybe I should do this next time we've crossed the limit. Actually, I should send you this paper and ask you to read the paper. I mean, this is like really tedious stuff. I have to cover it. It's part of the syllabus. Maybe I should just mention that you can check your medium is good by performing this experiment. This I have already shown to you. Maybe I'll show it to you graphically again. So if you have designed your medium well, then, let's say you're limiting carbon, so the limiting substrate is the carbon source. Then if you double the initial concentration of the carbon source, you should get double the biomass. because if everything works out well, then x max should be equal to ysx times s0 plus x0, where x0 is kind of small, so this is approximately equal to ysx times s0. So if your substance, if your medium is truly limiting in the carbon source, doubling the initial concentration of the carbon source will give you twice the biomass levels. It will not, so basically what I'm talking about is things will start to fail if this graph starts to change its slope. Then that means something else has become limiting. This I will pick up next time. So we'll leave it at this point. And I'll be adding this paper to files later on today. Okay, so you can start reading it. So for practical knowledge, this is theoretically, this is nothing, but from a practical standpoint, I would say this is one of the most important papers that I have read. Okay, so we'll call it a day and see you on Thursday. Thank you.
Yes, sir. Sir, I had a question.
Okay, sir.
Uh-huh.
Sir, so the minor, sir, so you will take it on the scheduled slot?
No, I cannot, right? How can I conduct a minor in
Yes, sir.
1 hour? I think there are 50 students. I mean,
Yes, sir. 50, 60
even
students.
if I keep 10 to 15 minutes,
Yes, sir. It will take a lot of time.
it will take me 8 to 10 hours.
So, sir, when would you, so like after the minor? Minor ends on 23rd September.
I'll have to check what the rules are. Do I have to complete it before the minor, or do I have
So,
to
I
give
mean,
you the?
sir, you can schedule it at any time, I think. But like not within the minor, I guess. Not within the minor time period. Because that would lead to slot crashes.
And so, does this mean that on the day of the minor, so the deadline was, basically 11 a.m. on
Yes, sir. On
the
20th.
20th.
Yes, sir.
So, do I have to provide you by that time? So, supposing I'm going to give you X questions. So, is that the deadline for providing the questions or the paper?
No, sir. That is
That
the
is
deadline for the
deadline for
end
the
of the exam.
submission.
Yes.
So,
that
or
is-
else what you can do is like you can conduct the test after 23rd, like
yes,
whatever date is
after
suitable
the
for you.
minor, after the all the minors are over.
Well,
Then you can.
I can provide you with. So, supposing I decide to go along with, I have 2 3 papers, right?
Okay, sir.
And I will ask you a question on one of the papers. You
Yes,
read
sir.
the paper, and I will ask you what you have understood of the paper.
Yes, sir.
I can provide those papers to you, basically, by that day, right? By
Yes, sir.
that deadline, and then the grading starts after the minors are over, in which I meet with people, X number of people per day.
Yes, sir. That would be okay, sir.
I will just check with the head and see if that's okay. But yeah, one-on-one interaction is best. I can find out within 5 minutes whether the person knows. Okay.
Yes.
So it would be some sort of a viva, right?
Yeah, because too much copying going on. I mean, I saw last semester almost. I could even pick up these 8 people have done it together. It was just a complete joke. So some people in the department just continue to do. They don't give a shit. They just keep on conducting courses. But to me, it seems that there is something wrong about giving cheaters an edge. So, I mean, one way is to punish them. That's a waste of my time, right? This course is a headache. Better thing is to just meet them for 5 minutes and I can tell what's going on. It'll be
Yes,
like a
sir.
viva.
That would be a nice idea.
Yeah,
So
I can
basically,
ask. Yeah, I can ask anything, right? I mean, I'm free. Whatever I've covered, I'm free to ask.
yes, sir. So basically, to summarize, you'll be providing us with 2 or 3 papers by like the scheduled minor slot, and after 23rd, you'll be conducting like one-on-one vivas where you can ask us to solve questions live, or you can ask us like few theoretical questions.
Yeah. I mean, so it could be, I can ask you to. I mean, I'm not comfortable just giving you these homework problems. I can ask you how you got it. I mean, and the reason is that these are also pointless, right? I mean, 3 guys, 5 guys sit down, you just tell him क्या किया तुमने दिखा दो. But I can pick up anything from the homeworks and say, tell me how you got it. I want to know what was your rationale. Why didn't you do it this way? You understand? Or,
Right, sir.
Yes.
and I will also throw in a couple of papers. That is to see if you understood what was done in the class, then you really shouldn't have trouble reading what people are writing. So I'll
Yes.
give you 2 papers. You pick one of them, or maybe I'll give you one of them, whichever way it is. And I can ask you anything from that paper. What is he talking? Why is he doing this? What does he mean? Is he wrong here? Is he right there? That kind of stuff. Okay?
Sir. And so the
Same.
weightage would be like the designated 50 marks itself.
Same, 33%. Yeah. But there is no fixed time. Meaning, if the person can't even answer the basics, I mean, it might end in 5 minutes. Some other people, I might talk longer for up to 15 to 20 minutes to probe deeper. Are you with me? So there is no fixed
Yes, sir.
time. It will all be, I will make it up as I go along. I have enough experience to know what to do. Don't worry. Okay?
Yes.
All right.
And
Thank
so
you.
there'll be like 2 tests or like 3 tests, 3 such tests.
2. I have not, one minor and one major, right?
Yeah, fine. So 50% weightage each. Right. Okay.
Right.
Fine. Thank you, sir.
Uh-huh.
So, thank you.